Okay, I'm going to run through the slideshow on Introduction to Organic Chemistry, which is basically just an overview of some of the big themes in organic and a basic idea of why you need this material. So we're going to go over some basic definitions, some basic skills, and then we'll get into the next video will be a little more detailed, and we'll talk a little bit more about the compounds that are classified as organic. So there is guiding questions at the beginning of this slideshow, and it points out to you some really important things that you need to make sure you pull out of this. Some are historical so that you can understand the way that the word organic has changed. And then some of them are contemporary, meaning that now the word organic is used in ways that we do not use it in chemistry. So you really need to know um, the difference. If you're trying to decode a question and you don't really know this material, you're going to come up with the wrong information because you're trying to base it on your everyday definition of the word organic, which is drastically different than the one we use in chemistry. So, basically, the original definition of organic is that organic molecules were believed to be molecules that could only be produced by living things. So, the word organic in biology, for example, actually refers to things that are alive or used to be alive. So, organic matter would be matter that comes from living things. So, like a plant dies and decomposes and makes fertilizer in the soil, that would be considered organic matter. So that was the original definition. And things like spider silk or milk, everyday things that you're around all the time, are actually produced by other living things. And so those were the things that were pretty much being studied by the scientists who were looking at organic chemistry in the beginning. And this goes back quite a ways. Um, so that definition gets thrown out probably in the early 1800s. So the first time somebody can synthesize, so the word synthesize means to make something. And when we synthesize things in the lab, they are lab made, meaning that they don't come from a natural source. An organism is not making them. So one of the things that you make organically in your body, a lot of living things do, would be urine. And urine contains a bunch of other chemicals that your body's trying to get rid of. One of those is uric acid. Now, urine was in use a lot, believe it or not. Um, it had a lot of household uses, cleaning uses, and also it was used to make military weapons. So if you didn't know that about urine, urine can be used to make gunpowder. It can be used to set the dye when you're dyeing garments, meaning like if you're dyeing something to make it a certain color, the dye might wash out, and the components that were in urine would actually help the dye to set, like make it stay in the fabric. Um, there were a lot of things people were doing laundry with urine, like kind of gross, but it was a source of chemicals that people couldn't make. They didn't know where to get them. Only people's body were making them, things like ammonia, which has bleaching properties. So he made this compound in the lab without a person having to make it. And this changes the definition of the word organic. So the word organic now in chemistry refers to an entire class of chemical compounds that are molecular. So remember, our classifications for compounds are ionic and molecular. Molecular compounds are composed of nonmetals held together with covalent bonds. Covalent bonds are bonds when atoms are sharing their electrons. These are called molecular because they form molecules. So if you do not know any of these words that I am saying, like what is a molecule, you need to make sure that you do a little background research and make sure you understand those terms because they're going to be in regular use at this point, and I'm assuming you know them. So the core backbone of all of these molecules that we consider to be organic are carbon based. You will sometimes hear people say we are carbon based life forms, and that's true. On Earth, The largest, most complicated molecules that make up living things are entirely based on carbon. And that's because carbon has some special bonding abilities that allow it to make really large molecules, like really large. Whereas inorganic compounds, like ionic compounds and stuff, the because they don't form really big molecules, or even just some inorganic molecular compounds like water, they can't get very big. And so without that level of complexity, you can't get big, giant, large organisms. You are built out of atoms. And so the atoms have to be made into something bigger to make you. So carbon's the key to this. So our definition of organic in chemistry is that a molecule has to have carbon in it to be organic. Now, here's an important point you want to probably write down in your notebook and remember when you're answering test questions. On a Regents question, if they ask you what makes this compound organic, just say it contains carbon. Okay, that's the answer. They are carbon-based molecules. That's why they're organic. I have to give you a little bit of extra background so that when you're identifying molecular compounds, you don't accidentally identify something that's not organic as organic. And that is really, really confusing. So, one of the little tips I'm going to give you is that you're looking for things that usually are pretty big and also contain hydrocarbon. Um, sorry, they are hydrocarbons because they contain hydrogen also. Um, so organic compounds do form molecules. In fact, the molecules are enormous sometimes. So this is why carbon can do this. Carbon is one of the only nonmetals that not only can it make four bonds, but for some reason, carbon atoms can do this in these long, long, long chains, like hundreds of carbons long. They're enormous molecules. And they can also do something called make ring structures. Now, they're not the only ones that can do this, but they're the most stable. And so in nature, carbon became the most prevalent atom to do this. So in labs, we have forced atoms like phosphorus and sulfur to form ring structures, but they're a lot less stable. Okay, so here's why I have to give you that little guide, because there are things that have carbon in them that are not organic. And one of them happens to be molecular, it's carbon dioxide. So carbon dioxide is not considered to be an organic molecule. So just to help you not pick that answer on a test, I want to remind you that you're looking for things that match up with definitions of what mostly hydrocarbons look like. So hydrocarbons are, we're going to learn about them soon in the next slideshow. They're compounds that are made predominantly of carbon and hydrogen, and so they're a lot larger. So one of the approaches to this is for you to also look for molecules that contain just carbon and lots of hydrogen. But again, if you're answering a test question and somebody says, hey, why is this organic? You're going to say because it has carbon in it, because that's the definition of an organic molecule. Okay. So this is the list of some things you're going to come across that have carbon in them, but they're not organic. So you do have to be able to tell the difference. Okay. So I actually had to ask myself this question. There's two topics in chemistry that sort of get shoved down your throat, and usually you rush through them. We don't in our classroom because I really hate teaching things that way. But in many chemistry classrooms, organic and nuclear are sort of like an afterthought, and you cram them in at the end of the year, and then no one really explains to you why you had to learn this. And the real reason why is because a majority of the chemicals that affect your life every day are actually organic. The medications you take are made by organic chemists. The materials you use all around you are predominantly organic in nature, and many of them are synthesized from or derived from hydrocarbons. They're taken from crude oil. And when I say a lot of things, I mean pretty much everything. All the plastic, chewing gum, medicine, pretty much everything. A lot of glues, a lot of things are organic in nature. Paint on your car, like I could go on and on and on. Just the number of plastics you interact with in a day. And so when we have conversations about using fossil fuels, and it's not a political stance, it's a it's a concern as chemists that we have, right? Chemists have had a huge impact on the world historically. The revolution in organic chemistry that started probably around the 30s, um, that changed the way people live. It changed the materials they had access to. It changed the fabrics that we use to make our clothes. It changed where we get cleaning supplies from, everything. And it's partially because we started using gasoline and oil as fuel. Previous to that, we were predominantly using coal and wood. Trains actually ran on coal and wood, if you can believe that, you guys. We had steam engines. Steam engines they burned coal. They didn't burn gasoline or run on electricity. So we started to look for other things we could do with all this oil we were pulling out of the ground. Previous to this, if you wanted to light a lamp in your house, it was run on lamp oil, and the lamp oil came from dead whales. So these things, I can't make this stuff up, you guys. It didn't come from sources like out of the ground. This really changed the way that we live. So a lot of other things are made from crude oil, from fossil fuels. So they're not predominantly used for fuel. Actually, a huge amount, I don't know the exact percentage, but a really large amount of the crude oil that we pull out of the ground is actually used to manufacture goods. It's not used to burn for fuel. However, bringing all of it into the world still means that you have to do something with it at the end. So, in order to help you understand a little bit better our kind of issues with fossil fuel, and also, be worrying about running out of fossil fuel supplies, releasing gases into the environment that are causing probably global warming, that kind of stuff is really important. The fact that most of the medications that you use are made by organic chemists, they're organic in nature. That means that if you decide you want to go into a field like pharmaceuticals, you're going to really need to know your organic chemistry, because that's what they do. That's who they are. Most people who make pharmaceuticals are in some branch of organic chemistry. So that's why making medications is so complicated. And we do have other environmental concerns. When plastic came into heavy use, that started actually around the 60s or 70s. Up till the 60s and 70s, a lot of things were still put in glass containers. But we did start one of the very first really popular things to be made synthetically and organically with organic chemistry. I don't mean organically like grown without pesticide, was stockings, women's stockings. Previous to the 1930s or 40s, when people started to make stockings, women's tights, basically out of nylon. Previous to that, they were made out of silk or wool. They were really expensive, and if you tore them or got a run in them, it was like a big deal. So being able to buy nylon stockings was a really big deal. In fact, back in the day, they made nylon stockings that were so strong that they lasted for years. They almost never wore out. And they ended up having to make them break more easily because they couldn't sell people more stockings because their stockings lasted so long that they didn't need to replace them. So now we make just an absolutely tremendous amount of things out of plastic. Everything's made out of plastic, everything's wrapped in plastic, everything's being put in a plastic bag. And we've run into an issue now where we don't know what to do with all the plastic that we've made. Literally, physically makes a lot of pollution, and there's just basically plastic everywhere. We like to think it's being recycled. It turns out a lot of it's not being recycled. So we kind of have a plastic crisis. We've also recently discovered that plastics, microplastics, little tiny pieces of organic plastics, um, are in our bodies, everywhere in our bodies, in our brains, in our organs, inside of our cells. We don't know what the impact of that is. So I'm not saying that that's bad. It might not be doing anything, but this stuff is actually getting into our bodies, and we don't know right now what's going to happen. So if you want to go into chemistry in the future, one whole really important field of chemistry is green chemistry. And that is trying to figure out how we can do this differently and trying to figure out ways we can reuse materials that we've already made so that we're sort of not stuck with it. So that's kind of where we're headed next. Try to keep in mind that, at the time that chemists did a lot of the things that they came up with in the 30s and 50s, and, when they came up with Teflon, when they came up with plastic, they didn't know what the long-term impact of those discoveries were going to be. They just knew that the material seemed really useful. They didn't know that the waste products were going to be possibly cancer causing. They didn't know we were going to end up with so much plastic. A lot of the stuff that came out of the bad use of chemistry, that was done in the interest of business, which is not the same as science. So when business people take things that scientists come up with and just try to make money off of them, they sometimes ignore the ethical and moral repercussions of that. And sometimes the chemists do too, because there's money to be made. So we do have some issues, and I think there's going to be fields available in the future for people to go into what do we do to fix those problems. So here's my big warning sign, and it is because the word organic in everyday language does not mean what it means in chemistry. And here's where I get a little bit cranky. We had that word first. Okay, the word organic is a science word. It meant first living things. Then in chemistry, it meant chemistry having to do with carbon. Later on, it became a marketing term because the word organic means living things. It became a marketing term synonymous with like natural and healthy. And so we now have a classification for fruits and vegetables grown in particular standards. Believe it or not, they're not actually grown without pesticide. They are grown with pesticide. They are grown only with the pesticides that they are allowed to use to be classified as organic. So when you see an organic label on something, that is not the way we use the word in chemistry. So please, please, please be careful. If you're not sure about this, you're going to want to make sure you really get this new definition down. It's new to you, but it is not a new definition. It's the original definition of the word organic, means a molecule that contains and is based on carbon. What we're using as the term organic now is not the right usage of the word. So this new halo that they've put on healthy foods, the organic terminology is different than what we use in chemistry. Okay, so terms like organic, natural, pure, those are just terms that were stolen by marketing firms in order to make people feel good about what they were eating. Um, there's a lot of different language used to sell people products like this is clean food, blah, blah, blah. Those movements have been around actually since the 1800s and the early 1900s. They're not new by any stretch of the imagination, um, but they've made them sort of trendy and marketable, and they make people feel good about products when they want to buy them. The definitions have nothing to do with the real terminology in chemistry. So just keep that in mind, right? So basically, there's a lot of things that are organic that you wouldn't want to eat. So gasoline you put in your car is organic, but don't eat it. Uh, Crude oil is organic. Acetone nail polish remover is organic, but it's not the organic that you're thinking of. So just make sure you got that down. So here's some skills that you got to make sure you know how to do before we move on. So um, we spent a lot of time when we were doing bonding, reviewing ionic and molecular compounds, naming elements, and then drawing Lewis structures. We're going to be building on that. So if you need to be able to do all of these things at this point in the year, being able to determine valence electrons and knowing the octet rule so that you understand if you drew a structure, if you gave everybody the right number of bonds, um, giving people prefixes and suffixes, understanding how nomenclature works. Nomenclature, remember, is the fancy word for naming things. Um, Making sure that you can read a chemical formula, making sure you understand the difference between a molecular and an empirical formula. At this point, and what you know, what a structural formula is, all this stuff, you're going to have to learn more that's based on all of this. So it will also give you a chance to review some of that, which is like, how do you draw structural formulas? How do you tell the difference between a molecular and empirical and a structural formula? And then also, we're going to add a whole new system of naming and a whole new uh, set of nomenclature rules. So that whole new naming system is called the IUPAC system, and you have to learn how to do that on top of what you already know. So that's it, you guys. That's the whole lecture. This was just a rundown to get you familiar with the basic definitions. So your notes don't really have to be long for this section, but some critical stuff you need to walk away with is the definition of organic. Let's go back to the slides that have some of the critical stuff on them, right? The definition of organic is that molecules that contain carbon are organic. Okay, they must be molecular, and they're going to also probably contain a bunch of hydrogen. Um, but if somebody asks you a question about if it's organic, you're going to say it's organic because it contains carbon. These are the special things about carbon that makes it an entire class of chemistry. That it makes four bonds because it has four valence electrons, that carbon can form very long chains, and that it can also form ring structures. And making sure you can recognize that not all molecules that contain carbon are organic. All right, so that's the end of that. I will see you at the next video.